I had told you in the earlier lesson that when using cross-validation, it becomes a little tricky to apply ROC charts in combination with cross-validation because cross-validation is using the default cutoff of zero point 0.5. Whereas with ROC charts, that's precisely what we are trying to do. We are trying to determine the cutoff. Okay, and let's think back a little bit as to why we are thinking about the cutoff. When we think about the cutoff, we are talking about the trade-off between true positives and false positives. Okay, that's really what the ROC chart is helping us with. Okay, and that is arising because we are essentially talking about saying that different types of errors don't have the same costs, right? Classifying a buyer as a non-buyer is not the same thing as classifying a non-buyer as a buyer, right? These are two types of errors that we can make, classifying a positive as a negative or a negative as a positive, right? False positive and false negative. When we use a cutoff of 0.5, we are effectively saying that both of those have the same cost. Okay, what if the cost is asymmetric? That's what we mean by asymmetric costs, right? That is, the cost of classifying a buyer as a non-buyer could be much higher than the cost of classifying a non-buyer as a buyer, or vice versa. It depends on the context. Okay, a false positive may be much more costly than a false negative, or vice versa. Okay, now what if there is a way by which we can reflect these costs and generate the tree which takes into account these costs? Okay, the rpart function actually has a way to do this, and that's what I'm going to examine now. Okay, so we are using library caret, library rpart, library rpart.plot, all from before, and we're reading the data. But this time, because we are going to indicate the different costs, the costs of the two types of errors, right? We need to explicitly set the factor levels of the target attribute. Okay, so this is what we've been doing earlier, and I've just been ignoring it. This is the reason I was doing that is exactly for this purpose. Okay, so MEDVCat is our target attribute. So I'm saying $MEDVCat is factor $MEDVCat, and I'm specifically saying the levels are high and low. Okay, now the order doesn't matter. It is just that we need to know what the order is. That's all. Okay, and don't confuse this with the positive or negative class. This has nothing to do with the positive or negative class. Okay, here we are just setting the levels explicitly. It could very well be set as low high or high low. It doesn't matter. It's going to only play a role when we specify the costs. Okay, and that's when we'll come back to this. For now, don't worry about it. We'll come back to this at the appropriate time and I'll talk about it. Okay, so we set the seed, we do the partitioning. This is all like before. Okay, now the change is going to come where we are determining, we are building the tree. We are saying, and I'm calling this as tree.base. Okay, that is, I'm going to initially generate the tree without indicating the costs. In other words, default cutoff of 0.5 and the cost of false positive is the same as the cost of false negative. So that is just as usual. So we are saying min split is 10, CP is 0, and we go and get a tree. We get a tree of size 10, and we then generate the predictions on the training data, type equals class. Okay, so we generated the predictions on the training data, and now we are going to do the error matrix. Okay, so I'm just printing it in such a way that I'm first saying all errors equal, and then I'm printing the error matrix, and we get this. Okay, so when the default cutoff is used and all errors are equal, false positive and false negative are equally costly, then we get this. Okay, this is just as a baseline. That's why I called it base. Now we are going to generate one tree in which we have asymmetric costs. Okay, and the way we specify asymmetric costs is what is coming up here. Params list, and we are saying loss equals matrix C0150. Okay, let's understand how to interpret this matrix. And it's saying by row equals true and n row equals true. In other words, we are saying these are four numbers, but interpret it as a matrix with two rows, right? And the values are given by row. In other words, 0 and 1 are the values in the first row of the matrix. 5 and 0 are the numbers in the second row of the matrix. That's all this is saying. Okay, so the four numbers, and we are saying we have specified the numbers of the matrix by row, and there are two rows, right? So there are two rows, which means that obviously each row has two numbers. So these two belong to the first row, these two belong to the second row. Okay, so that's what the matrix looks like, right? So 0, 1, 5, 0, 0, 1, 5, 0, right? And the 1 and 2 correspond to what? Okay, that is where our setting that we did earlier of the factor levels, right? Let me just go back here. This part, BH dollar MEDV cat is factor BH dollar MEDV cat level C high low. So we said high is the first level, low is the second level. Okay, so that's what determines how the matrix is interpreted. Okay, so we said high is first, low is second, high is first, low is second, right? So that is what the system is going to use that to interpret the costs, right? So this is how the cost is now interpreted. So it basically says the cost of classifying a high as a low. In other words, it's a false negative. The cost is 1. And this is a false positive. The cost of interpreting, classifying a low as a high, that's a high cost. It's 5 times more costly. Okay, that's a false positive. Is 5 times more costly than a false negative. Okay, so that is what this is. So now we again go ahead, generate the tree. Of course, this tree is different now because it's applying these principles, right? So internally, after all, remember there is the Gini index that's involved in all these computations. So what the system is actually doing is it is manipulating its calculation of the Gini index and the entropy based on these costs. Okay, once again, I'm not going to go into the underlying mathematics, but that's what is happening. It's adjusting how it calculates the Gini index based on these costs, and therefore it comes out with a different tree now. Okay, of course, we would expect that the error matrix that this tree gets is going to be different from this error matrix, right? This error matrix was based on symmetric costs, whereas this one is based on asymmetric costs of a certain type. Okay, so now when we go and find the predictions and we generate the error matrix, right? Since false positive is 5 times more expensive than false negative, right? So clearly the system is more prone to classifying something as a low rather than as a high, right? Because false positive is penalized. So it's going to be more careful when defining something as positive. Okay, later on I'll put up all the error matrices so that we can compare them. And then we go the other way now to say that a false negative is 5 times more costly than a false positive. So the 5 and 1 are switched, the error matrix is now switched. Okay, so we see here this is a false negative is 5 times more costly than a false positive, right? And the tree again comes out as quite different, and we now get this error matrix. Okay, so let's put them all together here, right? So with the symmetric cost, this is what you get. With asymmetric, notice that this cell is highly penalized, so the number of elements in this cell is going to go down, right? Because whatever goes into this particular position is going to be penalized. Okay, so in fact it goes all the way down to 0, right? And more of these end up there now. Okay, because its threshold for classifying something as high has gone up, so it classifies some of them as low, so low has gone up here. Okay, and if you change the cost the other way around, right, then anything that comes here is going to hit the cost because it's very costly. So then you see that reduces, this increases. Okay, so what we are seeing here when we supply a loss matrix is actually intuitive. It makes intuitive sense that this is how it is supposed to work.